Thank you for the introduction, and thank you for the invitation of this wonderful workshop. I'm Keisuke Konosu from the University of Osaka. So today I'll talk about the non-perturbative aspect of homotopy-algebraic approaches to correlation functions. This work is based on the paper published in JHEP in last year, and working in progress with Yuji Okawa. So let's start. So as in many wonderful talks, homotopy algebraic structure is universal in field theory due to the structure of the Batarin-Minkowski formalism. So when we have the BB structure, we can always transfer it to the L infinity algebra. But today we consider the cyclic infinity algebra for the convenience. This is the same reason as in the Yuji's talk. So let us recall the what is a cyclic infinity algebra briefly. So when we have the action S, we can transfer it to the this form. So let me briefly explain what this means. This phi corresponds to roughly speaking quantum field, and the phi is the element of the vector space H, which can be decomposed by Hn, which is indexed by the integers, and n is associated with Gauss number and anti-Gauss number and something like that. And for the people who knows the BB formalism well, this is the configuration space of the BB formalism. So this is the space for fields and anti-fields. So, and other component is omega, q, and mn, and q and mn satisfies the infinity relations, which appeared in many talks, and also omega, q, mn should satisfy the cyclicity. So this is the structure of the cyclic infinity algebra. And for the presentation, we consider zero-dimensional scalar field theory. That is, we don't have a space-time coordinate, and we just consider the integral, not the path integral. When we consider scalar field theory and some other theories with no gauge symmetry, we only need two spaces, H1 and H2. So H1 is for the space for scalar fields, and we denote basis vector by C, and we take this degree, this C by degree even. And H2 is a space for anti-field phi plus, and this is the basis vector D, which have degree odd. So let me explain S in detail. So in the case of zero-dimensional scalar field theory, we can we decompose phi by using the basis vector C and D. And then the coefficient appears in front of C and D. We identify the coefficient in front of C with the scalar field phi, and the coefficient in front of D by anti-field phi plus. And we also have simplexes form omega, and we define like this way, that is omega cc is equal to 0, omega cd is equal to 1, and dc is equal to -1, and dd is equal to 0. And there are operators q and mn. So first, q is a linear operator from H to H, describing free part of the theory. So we define this part is a free theory. And also there are operator Mn, and this is the multi-linear operator from H tensor n to H, describing the interaction part of the theory. So when we fix n, this part corresponds to the n+1 point interaction. So let me see the example for the of the simple model. So let us consider the quadratic scalar theory. So the action is given by this form, and we want to rewrite this into this form of the action, which appears in many talks. And as in the previous slide, phi is given by this. We note so in this part we omit the phi plus d because we just considering the very trivial theory. Antifield does not appear in the action, so we just consider phi is equal to phi c. And the simplistic form is this. So if we define Q and M3 like this, and we substitute these definition into here, we reproduce this action. We not and actually the action MCCC is non-trivial, but other action such as MCDC or MDDD and something like that vanishes. Also, we only have quadratic interaction Mn for n not equal to 3 should be defined to vanish. So let us check this satisfy the cyclic algebra. So for infinity relations, this is trivial due to the absence of gauge symmetry. So I don't present the infinity relation explicitly, but we have to act Q and M3, Q or M3 twice, but we only have the two spaces, H1 and H2, so we cannot act twice non-trivially. So infinity relations are satisfied trivially. And cyclicity can be confirmed by direct calculations. This is very easy. So this is the description of quadratic Euclidean theory in terms of homotopy algebra. So this is our formula for correlation functions, which appears in the UG talk. So let me explain roughly first, and in the later part of this presentation, we explain this in detail. So roughly speaking, the left-hand side is just the endpoint correlation functions, and the right-hand side is our formula. So I is just identity operator, and H is propagator, M is interactions, and U is the dual of BP Laplacian. And pi n and 1 is some operators in coalgebra, so this is irrelevant from physics. So if we know the action, we can construct M, and U is determined from omega, and H is just a propagator. So if we consider the kinetic term, we can construct H. So if we know the information of the action and transfer it to the homotopy algebra, we can calculate the correlation function by using this formula. And actually, in the previous slide, we only consider the zero-dimensional scalar case, but this formula is valid for any gauge fixed theories, and which I and Giorgio proved in the previous paper. So let me first summarize this talk. So motivation for homotopy algebra for me is to apply it to SFT. So, and but the analysis by homotopy algebra remains to be perturbative because many people use the homological perturbation lemma, but in homological perturbation lemma and also in the correlation function formula, this operator is important, but this operator is defined by expanding around the identity. So this is just the perturbative expansion. So we want to beyond the perturbative. And the intuition is that this is the inverse operator of I plus HM plus IH by HU at the perturbative level. So And in this talk, we try to extend this formula for non-perturbative case. And the key idea is defining non-perturbative inverse of this operator. And in general, it is difficult to consider such a difficult thing, but for the simple case, we can consider. So we focus on zero-dimensional scalar field theory in this talk. So this is the content of this talk, and let me explain about the perturbative correlation functions. So to explain this formula, we have to expand the space H. So we consider the vector space TH, which is the sum of tensor H, so which is H plus H tensor 2, H tensor 3, and something. And we contain H tensor 0. This is the equivalent to complex number and whose basis vector is given by 1. So, and as in the so in the action, we have the operator from H tensor n to H, such as Mn. So we have to generalize H. So we want to generalize this operator to the operator of TH from TH. So for this purpose, we introduce the projector pi n, which is the projection from TH to H tensor n. So, and then some class of operator in TH. And one is the identity operator on TH. So this is just the identity operator, and we denote this I by identity on H. And by using this identity, we define the identity of on TH like this. So, and the important operator is called co-derivation. And when we have Cn, which is the multilinear operator from H tensor n to H, we define the operation like this. Then the bold-faced operator Cn is called co-derivation. So, and Q and Mn in the action can be extended to the co-derivation. And we denote the bold-face Q and bold-face M in the co-algebra representation of Q and Mn. So co-derivation version of the Q and Mn. So, and here we have U, and this is different from co-derivations, and this is defined by product of two co-derivations. For the case of zero-dimensional scalar field theory, this is the product of the co-derivation C and D. This C and D is associated with the basis vector C and D, and the characterization of this co-derivation is given by these relations. And the important point is, so I didn't write in the slide, but U is associated with the symplectic form omega. So omega. So if you know their symplectic form, we can construct U. So in the last part of the formula, I don't explain yet, is H. And this operator is called contracting homotopy, which appeared in the Clinton-San's talk. And so we first consider the operator H from H to H, from H to H. So, and then we define H by this property. Here, I is the identity operator on H, and P is the projector onto the subspace of H. When we consider perturbative correlation function, we just take P to be vanished. And then we can construct H from this relation. And then we can extend the bold-face H on the space TH by this property. Okay. So okay. So let us consider that okay, so this is the, so then we can understand these operator in terms of the algebra representation. So if you know the action, we can we expand this operator from around the identity, and we then calculate the correlation function perturbatively. So let us consider the extension of non-perturbative one. So as I said, the intuition to resolve this perturbativeness is to construct the exact inverse of this operator. It is difficult to consider for general cases. So as I said, we test this argument when we consider the zero-dimensional scalar theory. The key point of is that H1 is a one-dimensional vector space. So in general, H1 is infinite dimensional space because, for example, d-dimensional scalar field, we have the space-time index, and the space-time index becomes the how to say, so due to the existence of the space-time indices, it becomes the infinite dimensional. But in the current case, we do not have the space-time indices, so H1 is just the one-dimensional vector space. So then we consider the space TH1, which is the some analog of TH, and we just take H1 tensor 0 plus H1 plus H1 tensor 2 and something like that. And then the operator F and IHUHM is the operator from TH1 to TH1. And H1 is just a one-dimensional vector space. So TH1 to TH1 can be rewritten as infinite dimensional matrices. This is the key point of the extension of the non-perturbative correlation function. So let us consider the linear operator A from TH1 to TH1. So when we act A onto 1, we can expand this A1 by using the basis vector of TH1. That is 1, C, C tensor C, and C tensor C tensor C. And similarly, AC and AC tensor C, AC tensor C tensor C, and some other higher operation, we can expand by using the basis vector of TH1. And then the coefficient appears, and we just identify this coefficient to the matrix element. So, for example, let us consider A32, and this is so when we act A onto C tensor C, we just write the row indices to 2, and when we expand AC tensor C by the basis vector of TH1, and when we focus on the coefficient of C tensor C tensor C, this is the C tensor 3, so we just write column indices 3. This is how to read the matrix element from the expansion of the operation to the element of TH1. So let us reinterpret the formula of our formula in terms of matrix element. So this is our formula, and this is the Lorentzian case, and in the Euclidean case, we simply replace this to minus h bar. Since phi is equals to bar phi c, and we just write the matrix element of F, a matrix form of F by Fij, which is then phi NF1 can be rewritten by Fn0 C tensor n. So we substitute these into here. We obtain this form of the formula. So this means that the endpoint correlation function of scalar field theory can be calculated by constructing the matrix form of F and read the element of N0 component. So to derive this F, we need the representation of the matrix I, Hm, and Hu. So let us construct a matrix description of homotopy algebra. So first, I is the identity operator on PH. So we just identify I to be the same as the identity matrix. Next, let us construct HM3 in the chaotic theory and HU. So let us see HM3. So the operation of HM3 trivially vanishes when the input is less than 2. So HM3 1 and HM3C and HM3 tensor C is vanishes. And the input is equal or larger than 3. The non-trivial action arises, and the output decreases from the input by 2, and this is the definition of the coalgebra calculation, and we have this form, and we explicitly substitute the definition HMC, we have this result. So we can write HMC in terms of the matrix element. HU can also be calculated and construct the matrix, and then we have this form of matrix representation HU and HM3 in the chaotic Euclidean theory. So by taking m squared equals to 1 and h bar is equals to 1, I plus HM3 minus h bar HU can be written in the matrix form. And this is the infinite dimension. And so the point is that to construct F non-perturbatively, this is just the matrix, so take the inverse matrix. But in general, it is difficult because this the size of matrix is infinite dimensional. So for the convenience, we truncate the size of matrix, and then we can calculate the inverse. So when the size of matrix is 25, we have this result. So this is the result for 2-point case and 4-point case. And this is a rational function, not just a polynomial of lambda. So it seems that it is different from just a perturbative expansion. And I will comment later on the validness of the meaning of the truncation. So when we take lambda is equal to 3, which is the region where the perturbative expansion apparently broken down, the exact value calculated by the direct integration by Mathematica is this value. And when we take the matrix size to be 1000, the 2-point function from our formula is obtained. So 2-point function of the formula is this value. So comparing these two, these results agrees with high precision. So, and this table represents the various lambda and various matrix size. So we focus on lambda is equal to 3. When the size of matrix is 10, the result is very bad. And when we take larger value of n, then the precision, the value approaches to the exact result. And finally, when we take n equals 1000, we have this result. This result reflects that so the exact inverse corresponds to the matrix size infinity, and we just truncate the matrices and increase the size of matrices, it approaches to the exact result. This is a numerical check, but it seems that our first intuition is correct. And so let me comment on the truncations. So our formula is supported by the algebraic Schrödinger Dyson equations, or given by this formula. And this is equivalent to the ordinary QFT Schrödinger Dyson equation. So truncating the size, matrix size by n means that we set the endpoint function is equal to 0 for n is larger than or equals to large n, truncating size. So, and actually the the work after our paper has shown that in the case of zero-dimensional chaotic Euclidean scalar theory, the result agree with the nonperturbative equation function, which is I think modified Bessel function, and in the large n, in the n goes to infinity limit. This is proved by these Barcelona people. So we just consider the truncation for convenience, but it may be interesting to consider such a direction for other cases. But anyway, at least for the chaotic Euclidean theory, when we take n goes to infinity, this is the non-perturbative result. So let us consider more non-trivial case. So in the previous perturbative equation functions, we consider the equation function around phi is equal to 0. And we can also consider the non-trivial around phi is equal to a, not equals to 0, and a is the solution of the equations of motion. So here, phi star is the co-derivation associated with phi star is equal to AC. So this is the classical solution, A. And these children are defined by this definition. That is, we just consider the action expanded around the non-trivial classical solution and construct the Moore-Cartan action as in the previous slide. So since our formula, so actually the more sophisticated formula is written in the paper with Yuji, but for the presentation, I just like the very easy and practical form of the formula. So if you have interest, please see our paper. But anyway, this is the formula around the non-trivial equations solution, non-trivial solution, and this formula states that our formula depends explicitly on the solution for the equations of motion. So we claim that this formula reproduces the equation function on the associated left-set symbol. So I will explain the precise meaning later. So before explaining our guess, let me explain what is the left-set symbol method. So when we consider the real scalar theory, in the left-set symbol method, we just replace the real variable to complex variable, and then solve the equation called downward equations, and z is parameterized some parameter t, and we just solve these equations. And this is the generalization of the steepest descent method. So, and when we solve these equations, the path Ji associated with the equation solution I of equations motion are derived. And the original contour, this is the original path integration path C, can be decomposed by using this solution Ji with integer Ni. And this integer can be determined from the just solving the another equation called upward equation and count the intersection number of the original contour, and then we know how to sum this Ji to reproduce C. So let us see the example for the easiest case. This is the Airy function. So first, let us consider the partition function of the Airy function on the real axis. When we consider the less simple method, the integration path split into two. So actually, we just consider A to be negative and solve the equations of motion. There are two solutions on the real axis. And solving the downward equations, we have two flow. This is called the symbol, J minus and J plus. J minus is associated with the classical solution, minus some coefficient square root minus A, and this part corresponds to plus square root minus A. And then this partition function can be decomposed into the integral on J minus and J plus. So we call these on the partition function on the symbol J minus and the symbol J plus. So, and we just write this part of the correlation function Z minus and this part on the Z plus. This minus and plus just is associated to the classical solution phi is equals to plus minus square root minus A. And the correlation function can also be decomposed into two parts like this. So this is the integral associated with J minus, and this is the integral on J plus. And we can rewrite this form into this form. This is just the straightforward calculation. And we just call this let and this let part by the correlation function on the symbol J minus, and the blue part we just call this correlation function on the symbol J plus. So we just denote this correlator plus minus by this definition. Our claim is so, and in the previous slide, our claim in the previous slide is that so we have the dependence of the classical solution in our formula. So when we choose phi star is equals to minus classical solution, our formula calculate this part of correlation function. And if we take phi is equals to plus square root minus A, our formula calculate this part of the correlation function. So this is just a numerical check. This correlator is just calculated by using Airy functions, and this correlator is means the just this is calculated by our formula, taking the matrix truncation and taking the inverse. So as you can see, the result agrees with high precision. So it seems that our conjecture are correct. And for concerning the consistency, let us go back to the previous case. And the first example corresponds to the case where only critical point phi star is equals to 0 contribute to the path integral. And our formula also works for Minkowskian quartic Euclidean, Minkowskian quartic theory. This corresponds to single symbol with trivial phi star in the Minkowskian signature, and Airy function with A is positive. this corresponds to the single simple case, but the non-trivial phi star. Also, this is the Minkowskian double Bell potential. This corresponds to the triple symbol. So in the Airy case, critical point was 2. So there are 2 critical points, and both of the critical points contribute to the calculation. And the double Bell case, there are 3, and all of the contribution is needed. So we can calculate this part in the correlation function of Airy function or some other correlation function non-perturbatively. But to consider the the full correlation function, we want the prefactors. So we want to know why we need to adapt this relative ratio in terms of homotopy algebra, but we do not know why. We do not know why we have to adapt with these factors only from homotopy algebra to present. So for now, admitting this fact that we have to adapt something like this coefficient, let us formally calculate this part of the relative ratio and in terms of homotopy algebra, and then we have the full correlation function in terms of, so we can calculate the full correlation function at least in terms of correlation homotopy algebra. So the Z plus over Z minus is the relative ratio of partition function for different theories, and this relative ratio can be seen as the interpolation of 2 theories by auxiliary parameter t. So for the so before seeing how to calculate z plus over z minus, let us see the more simple example, that is the interpolation between free theory and the chaotic theory. So we want to so the first goal is to calculate the relative ratio of correlation function of free theory and chaotic theory non-perturbatively. So for this purpose, let us consider the action of the one parameter family S of t, which is given by this. When we take t is equals to 0, we reproduce the Gaussian action. And when we take t is equals to 1, we have this chaotic action. So we first admit this form of partition function. And when we take logarithm and taking a derivative by auxiliary parameter t, we have this form. And integrating from 0 to 1 by t, we obtain this form. So the direct calculation of a partition function, we don't know how to do, but as in the previous slide, we know how to calculate the correlator. And this form of the relative ratio can be written in terms of correlation function. So we can calculate this formula, this part in terms of homotopy algebra. So let us rewrite this formula into the homotopy algebraic manner. And in terms of homotopy algebra, the action was written like this. So the difference is that we include the absolute value of this 0. Sorry, the part which is irrelevant from the field value is 0, and we just denote omega, bra omega by just this symplectic form. So this is almost the same in the previous slide. So this is the form of the action, and taking a derivative and substitute this into here, and the correlator can be replaced from F1. Then we have this formula. This formula is valid for general case when we interpolate the partition function from zi to zf by using s of t. And for more practical application, we can calculate the effective action of considering the action of the form like this. So this is just appears in the quantum field theory, and this corresponds to calculate j over z0. And the zj can be written by this form. We obtain this by applying our formula. We obtain this form, and applying our formula, we can see that we can see how to calculate effective action in terms of homotopy algebra. Actually, there are another way to construct this Wj, which appears in our LSD paper with Yuji, Shono, and Jojiro, appeared in previous last year. But so this takes other approaches, but we can check that these formula are equivalent. So this can be consistency check. So let us go back to the ARE case, and we also so we want to consider the relative ratio of the partition function around the minus symbol and on the minus symbol and plus symbol. So let us first consider the minus symbol. So the action is given by like this, and we just consider the interpolation like this. When we take t is equals to 0, we just consider the quadratic term of this part. So we just consider the interpolation of this theory and this theory. So then we just denote the partition function of this partition function whose action is given by this by z minus 0. And applying our formula, we have this form of calculation. So, and we can similarly, we can do the same things around on the less symbol, plus symbol, and we similarly interpolate two theories. One is the action around the plus symbol, and another is the just taking the quadratic part, and we just denote the quadratic part partition function by z plus 0, and then we have this form of formula. And by using these z plus over z plus 0 and the previous z minus over z minus 0, we can decompose z plus over z minus like this. So we know this part and this part, and so we additionally need this part, and we can consider this interpolation similarly, and we obtain like the constant term. So combining these results, the relative ratio of the correlation function of z plus over z minus can be closely written in terms of homotopy algebra. So, and this is so and numerically calculate this value. We see that this calculation is properly reproduce the relative ratio of the ARE function around the plus symbol over minus symbol. So for combining these results, so in the first part of the my talk, we can calculate this part and this part by taking the by choosing the classical solution, and in the latter part, I explained how to calculate this part in terms of homotopy algebra. So we then have the full correlation function in terms of homotopy algebra in the closed manner. So let us summarize and discuss some other directions and future works. So for the summary, we consider the equation functions in terms of homotopy algebra in zero-dimensional setting and consider the non-perturbative expansion. We claim that the formula reproduces the equation functions on the associated deficit symbol, and the claim is checked by numerically testing several examples. So, and we also discussed how to reproduce relative ratios for partition functions of different theories. So, one discussion is that our formula is supported by the algebraic, as I said, the algebraic Schwinger-Dyson equation is, formula is supported by the algebraic Schwinger-Dyson equations, which is equivalent to the ordinary Schwinger-Dyson equations. And we noticed that the Schwinger-Dyson equations or algebraic Schwinger-Dyson equations does not have the information on the integration contour, except that the integrand vanishes at the infinite boundaries in the path integral. So for example, we consider the wrong sign Gaussian and take some contour C. If you take C to be the real line, of course Z diverges. But to apply, so when we apply our formula, we somehow have the finite value, and that means that our formula automatically chooses the convergent path, which is the imaginary axis, not the divergent path, which is the real axis. And so this is some mysterious things, and also so let us turn the attention to the relative ratio of the partition function. So our formula involves the ds over dt, and this can be written in terms of homotopy algebra like this. And this is similar to a class of observable proposed by Irving, McAfee, Shinobu, and Boschmeller in the previous paper. So in their paper, when we take E to be this form, and En is the En can be En is cyclic, and this can be promoted to the co-derivation, which satisfies this relation. Mu is the auxiliary parameter, and M is the co-derivation, which encodes the original action information. And so this is the extension of the infinity algebra, and E is the sum of En. So if we satisfy this condition and cyclicity, and this is gauge invariant. So our example have no gauge symmetry, but taking En is equals to the Mn T over dt might be interpreted as observable of the theory, the interpolation theory. And another way, and further, our formula replace this phi to be the expectation value of pi, that is pi n plus 1 f1. So the possibility is that the relative ratio of different partition function is just calculating a quantum observable ST. But again, this is just, we have no gauge symmetry, so the invariance is trivial. So this is just the analogy, but it may be some meaning beyond the relative ratio of the partition function. So let me denote let me say about the future works. One is that we don't know why our formula is related to the Lefschetz-Simple method. So we want to understand the Lefschetz-Simple method from the homotopy-algebraic point of view. And based on the observation, the discussion we have made, I think we have to include the information for the boundary of the path integral in some way and extend the formula. Another thing is that the extension for the non-perturbative analysis of finite dimensions, which is just the d-dimensional scalar or some more non-trivial case. So in our case, we just use H1 is one-dimensional or finite dimensional. So I think it is difficult to extend it as it is, but our formula shows, so our observation shows that we have information of non-perturbativeness in our formula, so I believe it can be possible. And the last thing is that the relation to the quantum observable at the relation to the observable at quantum level. So this is what I talked in the previous slide. So this is the end of my talks. Thank you so much.